So taking the same data set and doing the standard deviation and mean value analysis on it, we're also going to talk about outliers once we get there. So to start, I'm going to need n again, which hasn't changed. So there are 20 data points here. I'm going to have to set myself up a chart so I can get the sum of x and the sum of x squared, so I can do the standard deviation calculation the tidier way, because I don't want to be subtracting a horrific average value from each data point. It just makes a mess. So I'm going to make myself a little tally chart. There are the particular x values. So what have we got here? We have 2s, 3s, 4s, 5s, and 8s. Those are the values that show up. And if I count them, there are 2 2s, there are 5 3s, there are 1, 2, 3, 4, 5, 6, 7, 8 4s, 1, 2, 3, 4 5s, and 1 8. So what I'm going to do then is I'm going to take the value and I'm going to do a little column here where I find out what the value of 2 2s would be. When you were doing this manually, you would have gone 2 plus 2 plus 3 plus 3 plus 3 plus 3 plus 3, and it's exhausting. And you can imagine that if this data set had 1,000 points in it, you would be on your calculator, right? This plus this plus this plus this plus this plus this plus this. And if you miss even one of them, you have to do the whole thing again. And that's exceptionally frustrating. So I'm going to try and organize my information here a little bit to avoid doing that. If you can see yourself doing this with your calculator, 2 plus 2, and then just sort of stop there. Well, 2 2s is 4. So I don't need to type that into a calculator. I can just do that in my head. These 2 2s, if I add them up, would be worth 4. These 5 3s, 3 plus 3 plus 3 plus 3 plus 3 is 15. So I don't need to put that in my calculator independently either. 4 8s or 8 4s would be 32. 4 5s would be 20. And 1 8 is just 8. So if I go through and I add these up, 4 and 15 is 19, plus 32 would be 51, plus 20 would be 71, plus 8 would be 79. So I have sum of x is 79. And I hope all of you at home are fact checking my numbers, because adding is hard for me. Anyway, here we go. The next thing I need is the sum of the x's squared. So if I squared 2, I would have 4. If I squared 3, I would have 9. If I squared 4, I would have 16. If I squared 5, I have 25. And if I square 8, I get 64. So when you were doing this in your list, you probably went through and squared all these numbers individually, wrote them down beside the numbers, and then again went through and went this plus this plus this plus this. And you probably had some trouble with this one because the numbers get bigger, and if you miss even one or mistype a 25 as a 35 or anything, then your standard deviation formula doesn't work. It's infuriating. So again, I'm going to try and manage the information a little better. I know that there's a 2 here and a 2 here, and if I square that, it'd be a 4 and a 4. So there's 2 4s. 2 4s is just 8. So you see what these headings are. This is n, the number of times it shows up, times the value. So I put it down. 2 times 2 is 4. This one would be the number of times it shows up multiplied by the data point squared. So 2 times 4 is 8. 3 squared is 9. There are 5 of them in the set. 5 9s is 45. 4 squared is 16. And there are 8 16s. 8 times 10 is 80, and 8 times 6 is 48, so that should be 128. 5 squared is 25, and there will be 4 of them in your list. 25 times 4 is 100. And 64, there's only one of them, would be a grand total of 64. So if I add these up, 8 and 45 is 53, and 128 would be 181, plus 100 is 281, 345. All right, so there I've got my sum of x and my sum of x squared. Now I can use that horrendous standard deviation formula, and since I don't need this chart anymore, but I do need the real estate it's on, I'm just going to clean that up for you and maybe try and erase and talk at the same time, which is challenging. It is late at night. There we go. So that standard deviation formula was sigma x is 1 over the number of data points square root n times the sum of the data points after they've been squared minus the sum of the data points before they've been squared, then squared, like so. So my standard deviation will be 1 over 20 times the sum of x squared, which is 345, minus 79 squared, uh, 20 times 345, 2 would be 600 and 6,900. And 79 squared, I'm going to cheat and use a calculator. Shh, don't tell anyone. Is 6,241. Oh, that should be in a square root. All right, so 6,900 minus 6,241 is going to be 559. Nope, that's not right. So let's just again use the calculator. Shh, no one will know. 659. And I'm not even going to try to square root 659 because that would be insane. So no offense to those of you who did do it in your head. Square root of 659 is 25.67. Divided by 20 gives me an approximate value 1.283. 284 if I round. Lovely. So over here, I'm just going to take note of some values. So I had an average, oh, what was that? 79 divided by 20. Once again, this is a handy little machine to have down here. It'd be 3.95. And I have a standard deviation of 1.284. And I have a whole bunch of stuff written on the screen here that I don't need anymore. So I'm just going to erase that for you. Now, what we're going to do with that standard deviation and the average is something very similar to what you did with your median and your interquartile distance. And that's go from that middle value up and down a certain number of steps to decide how far out we can go before something becomes an outlier. So for standard deviation analysis, what you're trying to find is a data point with a z-score of 3. So the assumption is that these data points are normally distributed, and if you don't know what that means, that's okay. It will be in the Khan Academy stuff and you'll come across it shortly. And a Z value of 3 means that you have got 99% of the data points. So when you have something with a Z score more than that, you're dealing with the smallest 1% or the highest 1% of the data points that would be in that distribution. That's a lot of jibber jabber. The point is, if you go from this mean value and you take this step 3 times up, then you will have found the place where your outliers start. So I'm going to do that. I'm going to take my x average and I'm going to add 3 standard deviations. So my average was 3.95 and my standard deviation is 1.284. So 3 times 1.284 is 3.852. And if I go from my average value of 3.95 up these 3 standard deviations, I would end at 7.802. So any number in my data set that is higher than 7.802 can be labeled as an outlier. And there's that character there who's taken 8 slices of bacon. 8 is more than 7.8. So this particular individual could be considered an outlier. So if you check the top, you should check the bottom. So let's go do that. So to check on the low end, you start at your average value, and then instead of going up 3 standard deviations, you go down 3 standard deviations. So if I do that, my average value was 3.95. My standard deviation was 1.284. And it's occurring to me that I shouldn't have erased those numbers. I should have just changed the sign, but that's okay. You like to watch me use the calculator anyway. So here I go. 3 times 1.284 is 3.852. And if I did 3.95 minus 3.852, I get 0.098. So any data point in this set that is less than 0.098 could also be considered an outlier. So you check down there, and this isn't anywhere close. So there are no outliers on the low end, but there's this one on the high end. Now that we've done that, you might ask yourself, well, what happens if I do find an outlier, like this person with their claw full of bacon? Well, you have an excuse in this calculation with the standard deviations to say that this person, because they are so far away from the average, can be considered statistically erroneous, that I can scratch them from the set. So let's just do that hypothetically. Look, there he goes. The bacon police show up and say, no more claws for you, and you eject them from your establishment. You might notice that there are no longer 20 data points in your set. You might also notice that the sum of x is no longer 79 and the sum of x squared is no longer 345, which means that your standard deviation is no longer 1.284, nor is your average value 3.95. So all of this work that you've done has to be done again, because you have a new average and you have a new standard deviation. Don't do that. If you find an outlier in the exercises that we're doing, that's okay. You just identify it as an outlier, and please do not repeat the exercise. But if you find yourself working, earning 6 or 7 figures working for a massive corporation or anyone who's paying you to do this sort of analysis, and you find a number that's an outlier, it would be due diligence, right? You need to try and do the analysis again without that person, right? Like, you've essentially said, I have a mathematical excuse to say that claw hands at the buffet table shouldn't be accounted for when I'm trying to decide how much bacon to make. So if you do that, then you should toss it from your set when someone's paying you to do it, because it's going to take you a lot of time. I think that's all I have to say about that. So when you're doing the standard deviation and mean, you find the mean value, and then you go either up 3 standard deviations or down 3 standard deviations in order to find your outlier.